Welcome everyone to another Deep Dive Explainer. I am absolutely thrilled you're here today because we're going to unpack one of the most fascinating engineering feats of our entire generation. Consider me your documentary guide as we explore the complete physical and digital supply chain of space-based internet. We're literally going to trace the unbelievable journey of a single byte of data and the hardware that carries it all the way from a busy factory floor up into the freezing vacuum of space and then straight back down to that little device sitting right in your hands. Okay, let's dive into this. Here's the spatial journey we're going to follow today. First, from factory to pad. Second, liftoff and orbital deployment. Third, the evolution of the constellation. Fourth, the space-to-ground network. And finally, the end-user experience.
All right, starting with Section 1, from factory to pad.
Let's kick things off with Phase 1, which is just getting all this hardware built and ready for the launch pad. Now you have to understand, the sheer scale of mass production required for a mega constellation like this is just mind-boggling. It demands a completely different approach than traditional aerospace manufacturing. So to pull this off, SpaceX uses a really clever dual-hub manufacturing strategy. Up in Redmond, Washington, they've set up a high-volume facility dedicated entirely to the satellites. We're talking assembly line production techniques for complex spacecraft. That drives the cost down to just a few $100,000 per unit, which is wild when you compare it to the hundreds of millions normally spent on geostationary satellites. Meanwhile, down in Bastrop, Texas, they're mass-producing the user kits, the hardware you and I actually buy, but doing it at the scale of everyday consumer electronics.
So once they're built, these satellites head over to the pad to meet the Falcon 9. This is the world's first orbital-class reusable rocket, and honestly, that reusability is the economic engine making this whole network possible. The launch sequence itself is just a masterclass in precision. Right after liftoff, the rocket hits max Q. That's maximum mechanical stress, just 1 minute and 13 seconds in. Then, stage separation happens at 2 minutes and 36 seconds, which lets that first stage drop back down to Earth to be used again. The fairing, basically the protective shell around the satellites, deploys a minute later. And then, about an hour and 1 minute into the flight, this incredibly dense payload of stacked satellites is deployed into orbit at an altitude of 290 kilometers.
Moving right along to Section 2, liftoff and orbital deployment.
Okay, so the rocket's job is done. The fiery, chaotic part of the launch is over. Now these newly deployed satellites have to survive and operate in the harsh, absolutely silent vacuum of space. But at 290 kilometers up, they're actually still way too low. They need to move. To do this, they fire up their Hall effect thrusters. These are super efficient electric propulsion systems that run on krypton gas or argon in the newer models. Now, they don't give you a massive fiery burst of speed. Instead, they're low thrust but incredibly efficient. Over the course of about 1 to 4 months, these thrusters just slowly, steadily raise the satellites from that 290-kilometer deployment altitude up to their operational homes at 550 kilometers or even 350 kilometers for the newest generation. And crucially, at the end of their 5 to 7-year lifespan, these exact same thrusters are used to safely deorbit the satellites so they burn up completely in the atmosphere. No space junk left behind.
But think about this for a second, because here is a massive logistical nightmare. SpaceX currently has over 10,000 active objects up there in low Earth orbit. So how in the world, or rather how in space, do thousands of satellites manage to navigate autonomously? I mean, how do they avoid constantly crashing into each other without an army of humans sitting at desks flying them with joysticks?
Well now, what's really interesting about this slide is how it breaks down the answer. These satellites basically act as self-managing nodes. They use custom-built optical star trackers, which are basically cameras that survey the stars to figure out their exact orientation and altitude. Then they combine that with GPS and inertial measurement units. But the real magic? They continuously ingest live conjunction assessment data directly from the U.S. Department of Defense's Space Surveillance Network. Fusing that military tracking data with their onboard sensors lets the satellites autonomously perform evasive maneuvers to avoid collisions. Zero direct human intervention required, it's totally automated.
Which brings us to Section 3, evolution of the constellation.
Because SpaceX literally owns the rockets they fly on, they can launch constantly and iterate their hardware at breakneck speed. And this continuous, relentless upgrade cycle is for sure their absolute greatest weapon against well-funded competitors like Amazon's recently rebranded Amazon Leo project. Just look at how dramatically the hardware has scaled up here.
The early V1.0 satellites were relatively light, weighing 260 kilograms. Then the V2 minis jumped to about 740 kilograms, giving us roughly 80 gigabits per second of downlink. But the upcoming V3 satellites, they are absolute behemoths. They clock in around 2,000 kilograms, they switch over to those argon thrusters we mentioned, and they feature a massive silicon refresh that pushes their downlink to an astonishing 1,024 gigabits, literally 1 terabyte per second.
When you actually do the math on that, it represents a staggering 100 times total capacity leap for the network. Let me break that down for you. Each single V3 satellite carries more than 10 times the bandwidth of a V2 unit. But because SpaceX also plans to deploy 10 times as many of them into orbit, that aggregate network capacity multiplies to over 100 times what it was. It's a complete top-to-bottom re-architecting of the network ceiling. But, of course, there's a catch. At 2,000 kilograms apiece, these V3 satellites are way too big to fit inside the Falcon 9 rocket. So the entire V3 upgrade is completely dependent on SpaceX's next-generation rocket, Starship. Starship has this incredibly cavernous payload bay that allows it to launch 60 of these massive V3 satellites in a single mission. Think about that. A single launch adds 60 terabits per second of capacity to the global network. That is a structural launch efficiency that literally no other competitor on the planet can even come close to matching right now.
Let's move on to Section 4, the space-to-ground network.
Okay, so we've got these incredibly powerful machines flying around in orbit, but how does your YouTube video or email actually get from them to the wider internet? And this brilliantly illustrates the two primary routing methods they use. The traditional method is called bent pipe, where the satellite basically acts like a giant mirror. Your dish sends a signal up to the satellite, and the satellite immediately bounces it straight back down to a nearby ground station. But notice the dashed lines between the satellites themselves. Those are inter-satellite links. It's a much newer technology that allows the satellites to essentially play hot potato with your data, passing it across the sky from one satellite to another before finally dropping it down to Earth.
But eventually, all that data has to land on the ground somewhere. Enter the gateway terminals. These massive ground antennas are the absolute crucial, unsung heroes of this entire operation. They catch those signals from space and are directly, physically wired into our high-speed terrestrial fiber networks. I mean, without these gateways seamlessly plugging the space network into the physical global internet backbone, none of this would work at all. It'd just be a bunch of data floating in the void.
But here's a fun scenario. What happens if you're on a boat in the dead center of the Pacific Ocean, where there are obviously no gateway terminals to bounce the signal down to? That is exactly where those inter-satellite links come in, and they are powered by optical space lasers. Yes, actual space lasers. Each newer satellite is packed with 3 near-infrared laser units capable of 200 gigabit per second transfer speeds. They essentially weave together a distributed mesh network in space, letting satellites talk directly to each other. So your data gets routed over oceans and remote dead zones, laser to laser, until it finally reaches a satellite that does have a ground station in its line of sight. It's pretty amazing.
And finally, Section 5, the end user experience.
Let's bring the narrative right back down to Earth. All of this mind-blowing space infrastructure exists for one single purpose: to deliver the internet to you, the user. So let's look at the actual hardware that everyday consumers touch and interact with in their homes. A standard kit comes with 2 distinct pieces of hardware, and this actually confuses people all the time. First, you have the dish. This is an advanced electronic phased array antenna operating on the 10 to 12 gigahertz Ku and Ka bands. Its only job, literally its only job, is to communicate with the satellites in space. It does not provide Wi-Fi to your phone. The second piece is the router. The router takes the internet connection from the dish and broadcasts an 802.11 Wi-Fi signal on your standard 2.4 and 5 gigahertz bands so your laptop and phone can connect. So the crucial point is, if your Wi-Fi signal is too weak to reach the guest house, moving your satellite dish out in the yard won't help you. You need to move the router.
And you know, the user hardware is evolving just as frantically as the satellites are. Actually, here's a really surprising fact for you. Oleg Kutkov, who is a brilliant repair expert operating out of Ukraine, recently dug through some leaked firmware code and discovered an unreleased Rev 5 standard dish. Based on the firmware mapping, this next-gen dish looks to be physically smaller, with the CPU and memory components moved unusually right to the dead center of the board. But fascinatingly, it appears to completely lack a traditional GPS receiver. This strongly implies the dish might start using the satellite constellation itself for geolocation instead of relying on traditional GPS. Talk about a self-sufficient ecosystem.
So all these upgrades, from the massive V3 satellites down to the clever Rev 5 dishes, they all culminate in solving the single biggest historical flaw of satellite internet: latency. Latency is just the delay in data transmission. Traditional geostationary satellites sit so incredibly far away that a round-trip ping takes over 600 milliseconds. It's laggy. The current 550-kilometer low Earth orbit dropped that lag down to a highly usable 25 to 60 milliseconds. But those upcoming V3 satellites, they're going to operate in a very low Earth orbit of just 350 kilometers. And since light travels at 300 kilometers per millisecond in space, dropping the altitude that much means minimum latency could actually fall below 5 milliseconds. That is fast enough to rival terrestrial, wired fiber connections.
This rapid, breakneck advancement is exactly why the global competition is heating up so fast right now. As this quote perfectly summarizes, the race is absolutely on for who will own the sky. Look at Amazon. They recently acquired Globalstar for nearly $11.6 billion just to accelerate their Amazon Leo network and grab up crucial direct-to-device spectrum. Direct-to-device is the brand new battleground here. It's going to allow standard, everyday smartphones to connect directly to satellites acting as cell towers in space, which could literally eliminate mobile dead zones across the entire planet.
Which leaves all of us with a truly profound question to ponder as we wrap up. For decades, satellite internet was always the slow, clunky, expensive option of last resort. But with this V3 architecture poised to deliver terabit speeds and sub-5 millisecond latency, are we witnessing the exact moment where traditional physical fiber optic cables finally face an unbeatable competitor raining down from the sky? I don't know, but it is an incredible time to be watching this engineering unfold. Thank you so much for joining me on this explainer today. Keep asking questions, keep exploring, and stay curious. I'll catch you in the next one.